So in this video, we're going to further discuss the Lagrange error bound. This is a consequence of Taylor's theorem. The purpose, again, of Taylor's theorem is to estimate the value of some more complicated functions over various intervals. We do this by estimating them with much easier functions to work with, which is a polynomial. Taylor's theorem states that any function can be expressed as a sum of polynomials. So what's the motive and the logic behind doing that? Well, it's much easier to work with polynomials than it is with some more complicated functions. Now, the trade-off to that is that they're just an estimate of that function, they're not its actual value. So there will always be a remainder. And obviously we're going to be very interested whenever we come up with an estimate of, well, how close are we? Is our estimate a good one, or is it very, very far off? So the Lagrange error bound comes into play by basically telling us the maximum possible value for our error. Obviously, if that value were very large, we would want to continue getting a better estimate. We want to make the error as small as possible, and obviously we don't want to be off by much. We do this by essentially finding the very next term in the Taylor series expansion and asking, how much of an error could that possibly give us? If we know the worst case scenario, well then we can determine whether we're okay or not. So let's look at Taylor's theorem. Taylor's theorem states that any function f of x can be expressed as follows: f of a plus f prime of a times x minus a plus f double prime of a times x minus a to the second power over 2 factorial plus dot dot dot, and our general term, we have the nth derivative of f at a times x minus a to the nth power all over n factorial. Then we have plus our remainder. Now, there's a few things to note right off the bat. This is a more general way of doing it, and this is one said to be centered at a. There's a special case of this where a happens to be 0. That's called a Maclaurin series, which we very commonly work with. Taylor's theorem is a little bit more general and assumes that that could be centered at any point. So let's take a look at this. If we were to draw just an arbitrary interval here along the x-axis, we'll call that a right there, then x represents this right here. Any value and the length ultimately between a and the end of that interval. That's why we say it's centered at a, because on either side of a is the length x. You can go in a positive direction or a negative direction. One where a happens to be 0, and we draw an interval around 0, that's what we're looking at with a Maclaurin series. The Lagrange remainder theorem says that there is some point in this interval right here where you can maximize the error. It may be either a or x, but it does not inherently have to be. Usually it will be, though. So let's look at the Lagrange error bound formula. This says that r of n plus 1 of x, and we denote that n plus 1 to denote the next term over the last n we chose here in our Taylor series. So we take the n plus 1th derivative of a point c over n plus 1 factorial x minus a to the n plus 1. So it's very clear that this is just the very next term in our Taylor series polynomial, with one exception. Here we have c, here we have a. Why do we have that? Because it is saying that there is a certain point right here, c is going to be between a and x, where this value here is maximized. Some value in here allows this remainder to equal everything that's left. It will in all likelihood be either x or a, but it does not automatically have to be. So if this is the formula for finding our actual error right here, we may or may not be interested in computing the actual error, and we may also not be able to. So it often serves the purpose just to know a rough estimate of where we are. What is the worst possible scenario? How far off could we possibly be? If we know that that's acceptable, then we know we're okay. If my objective, for instance, is to be within 1 in 100, then all I'm interested in knowing is how bad could my error possibly be, and is that number more than 1 in 100? If it is more than 1 in 100, I probably need to compute my actual error or continue with my Taylor's series expansion to get a better estimate. But if I know the worst it could possibly be is already within an acceptable limit, then I know I'm good. So the way we denote this is to say the absolute value, because when we're dealing with error bounds, we're just interested in quantity, not direction. It doesn't matter if I'm off this way or this way. All that I'm interested in is the magnitude. We say that's bounded by the maximum value of the n plus 1th derivative of the n plus 1th derivative at c times x minus a to the n plus 1 over n plus 1 factorial. So this is the Lagrange error bound. So whenever we're looking at an example of this, we're typically going to be given an interval to work with, and we're going to attempt to maximize that derivative over that interval. If we do not get a specified interval, we're just going to have to essentially ask ourselves what is the maximum value that that next derivative could ever possibly be over any given interval.